So today we'll discuss rational functions and their graphs. We know a rational number is just a number that is made up of a fraction. Rational functions are no different. They're functions that are made up of a division of two or more polynomials. So these graphs will look a little more complex than what we're used to graphing. We're going to use some knowledge from our graphing of polynomials to help us along the way to graph these things. Some commonalities that they all have in common is you'll notice that each of these graphs have an x-intercept and a y-intercept. This one happens to be the same. There's your y-intercept here. This actually has two x-intercepts. And as we know, we'll always find x-intercepts by setting y equal to 0. Right? Then we find our y-intercept by setting x equal to 0. Then you could do that in each of these two problems and see where those come out. Now these lines right here are the things of curiosity. These are all called asymptotes. And they have some things in common, and there are also some differences depending on which asymptote. There is something called a horizontal asymptote and a vertical asymptote. Now, let's start with the verticals first. Vertical asymptotes act like barriers, all right? They are lines that indicate where the function is undefined. Okay, now a function can be undefined a couple of different ways as far as domain goes. But the way we're going to look at it, since we're dealing with fractions, we know that in a fraction, if you have 0 as a denominator, your fraction is going to be undefined. So these vertical lines or vertical asymptotes describe what x value would give you a 0 in the denominator. So in this one, it appears to be 2. If I put 2 in here, that is undefined. So I have a vertical asymptote here, and in this case, it's 1. Put 1 in, that's 2 minus 2 is 0. So that would be undefined, and negative 2, so 4 minus 2 minus 2 is 0. So again, vertical asymptotes. So again, the vertical asymptote, where function undefined. And you'll notice also that the graphs will never cross those vertical asymptotes. So you'll see this part of this graph goes towards that asymptote, but it'll never cross it. This part of the graph goes towards that asymptote, kind of hugs it as it goes up, never crosses. Likewise, this one will get close to the asymptote, never touch it. And you can see the same thing on this side. Now, horizontal asymptotes are going to, again, like vertical asymptotes, be kind of like boundary lines, but they aren't stopping points like the vertical asymptotes. They don't tell you where the graph is undefined. What they do is the horizontal asymptotes describe end behavior. And we've discussed that before with our polynomial functions. So if you look at this graph, you'll notice, well, let's start here. You'll notice in this graph that this line appears to go out to infinity. So as x goes to infinity, y ends up looking like it's going to 1, half actually, because 1 would be right here. And as we go to negative infinity, y goes to negative half. So that line describes what the graph is going to as x gets very large, both positively and negatively. It doesn't talk about what's happening in the middle, and you can see that here because in this graph, you'll notice the graph actually passes through that horizontal asymptote, whereas this one appears not to. But you'll notice as x goes to infinity, on this guy, we appear to go to 2 for y. And even though this crosses, you'll see it comes up and it starts going back down and hugging. And as x goes to negative infinity, y as well goes to 2. So again, these horizontal lines describe end behavior. You can cross them, but in the end, the graph is going to get very close to that line. So let's talk about some rules for graphing these things. The first thing we're going to do is we're going to find the intercepts. Then we're going to find the vertical asymptote by finding what makes the denominator equal to 0. And then we're going to find these horizontal asymptotes. And there's a couple of rules that we're going to use today. There's another rule that we'll use tomorrow. But let's use these rules for today. So if the degree, the highest power of the numerator, is less than the highest power of the denominator, your horizontal asymptote's automatically equal to 0. If the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote is going to be the division of the leading coefficient. So let's just, now that we know this, go back to our previous example and look at these horizontal asymptotes. In both these cases, we have degrees that match. So in this case, leading coefficients are 1/2, and that was the end behavior, or the horizontal asymptote. In this case, matching again. So if I distribute this 0.5 through, 1 divided by 0.5 is 2, and the horizontal asymptote was at 2. So that follows these rules that we just described. Next, you're going to sketch whatever you absolutely know based on what you're given, and if you can't complete the graph by then, you're going to plug in some points as needed, and I'll show you how to do that in our next examples. So we'll start out on the easier side. The first thing is we're going to find the x-intercept by setting y equal to 0. So 0 is equal to 3x plus 5 over x plus 4, multiply, get 0 equals 3x plus 5, x equals -5/3, y-intercept, set y equal to 0, or I'm sorry, set x equal to 0, and you'll notice that we get 5/4. Vertical asymptotes, set the denominator equal to 0, because we want to know when that equals 0, and we get -4. And a horizontal asymptote, we've got to take and check the degrees. They're matching. So in this case, divide the leading coefficients, and y is equal to 3. So next, we'll take and sketch a graph. Let's draw a grid like so. I'm going to draw a vertical asymptote at -4. Let's go right around here, call that -4. Horizontal asymptote at 3. I'll label those -4 and 3. I'm going to throw in a y-intercept of 5/4, which is a little over 1, and I'm going to throw in an x-intercept of -5/3. Here's 2, -5/3 right around here. All right, now, at this point, I believe I have enough to graph this function. The only place it's undefined is this line right here. I know these points are going to connect, all right? And I know that I'm going, as x gets very big, I'm going to approach this line, so I'm going to draw this out this way, kind of hug the line. I know for a fact that this graph goes through here because I have a multiplicity of roots. Think about this. The root here was -5/3, so I know this has to go through. It's an odd multiplicity, power of 1. And then on this side, I know it can't be graphed down here, because if it could be graphed down here, it would go through the x-axis, and I don't have any more x-intercepts, so I know the graph has to be up here. And that's my graph. Again, we're not worried about being super accurate, just the general shape and which quadrant, if you will, or side of the asymptotes that the graph is on. Okay, so in this case, again, we're going to find the x-intercept, set y equal to 0. This brings about an interesting situation, because if I multiply this to the other side, I get 0 equals 10. So there are no x-intercepts. The y-intercept, we set x equal to 0, which gives me a 2. All right, next we're going to find the vertical asymptotes. We set the denominator equal to 0. It's going to need a factoring. So I have x minus 5, x minus 1 equals 0. Therefore, I have 2 vertical asymptotes of x equaling 1 and 5. And then the horizontal, we have to look at the degrees. You'll notice here that this degree of x is actually x to the 0 power. And anything to the 0 power is 1. That's why there's no x here. And this is x squared. So clearly the degree of the denominator is greater than the degree of the numerator. So y equals 0 is our horizontal asymptote. Let's set up a graph again. And we'll pop in our vertical asymptotes. Here's one at 1. Here's another one at 5, let's say. Horizontal asymptote is at 0. Close enough. Move it a little bit to make it a little more accurate. Or maybe we can't. Yeah, it's close. All right. And we have some intercepts we can take care of. Y-intercept at 2. And there are no x-intercepts. This is significantly more difficult to graph because there are no x-intercepts. So what I can tell you at this point is it will never cross this axis. Therefore, I know this has to go up and approach that line. And as x gets to negative infinity, I have to go to 0. So it's got to look like this. The rest, I'm not sure about. So I'm going to have to actually pick some points. So here's what I'm going to do. I know this is 1 here. This is 5 here. I'm going to see what happens at 3. And I don't really care about my actual number. I just care about whether it's positive, meaning above this x-axis, or negative below this axis. All right. So in the numerator, I get a positive number. In the denominator, I'm going to plug it into this because this is my denominator. 3 minus 5 is a negative, and 3 minus 1 is a positive. So I end up with a negative number. Therefore, I have something down here that's got to look like this. Again, it can't cross because there's no x-intercepts. And then over here, I'm going to pick another number, just an easy one, like 10. And again, the numerator gets me a positive. The denominator gets me, here's a positive and a positive. So that equals a positive. So therefore, this graph has to look something like this. All right, let's continue. So you'll notice right off the bat that we've got even degrees, so I'll be able to find something pretty easy. Quadratic down here, which means we're likely going to have 2 vertical asymptotes. So once again, x-intercept. You'll notice that every time when we've done this, the denominator has gone away, which means we're just basically setting the numerator equal to 0. So x equals 0 in this case. The y-intercept is also going to be 0. Because you plug in 0 for all the numbers and you get 0 over something. It's 0. Vertical asymptote, setting 2x squared minus x minus 10 equal to 0. Got 2x and x. I've got a 5 here and a 2 here. I need that 5 to be negative, 2 to be positive, so I have 5 halves and negative 2 for my lines on the vertical asymptote. My horizontal is just going to be, since we have the matching degrees, the division of the leading coefficients, which is 2. I'm going to set up our graph again. Now we'll draw in our asymptotes. We've got negative 2. Let's call this right here. We've got 5 halves right around, let's call it here. We set our horizontals at 2, call that right here. And let's label this. We have negative 2, 5 halves, 2, x and y intercept of 0. All right, so now Again, I know a little bit about this right off the bat. And you would think I would know something about this point here, but I actually don't. So we'll have to discuss just a little bit. I know for a fact that the graph can't be down here because it doesn't pass the x-axis. So it has to be up here. I know for a fact the same is true on this side because it doesn't cross the x-axis. There's no x-intercepts. So it has to be here. Now, I know it goes through this point, but I don't know if it goes up here or if it goes like this or if it goes like this. Well, one thing I do know is that my root has a multiplicity of 2. So it's going to bounce off this. So it's either going up or it's going down. And to find out which it does, I'm going to take and go f of 1, let's say. So when I plug into the numerator, I get a positive. When I plug into the denominator, again, I'm going to plug into this guy. Plugging in a 1, I get a negative and a positive, so I get a negative. And this guy has got to go down. Again, I'm bouncing off that because I have an even multiplicity of my x-intercept root. Lastly, I'm going to just take and factor this first just for funsies. I usually do that anyways. And then we'll go x-intercept. Again, we're setting 0 equal to x minus 3. So 3 is our x-intercept. Y-intercept. Set x equal to 0. I get 3 again. But this time it's a y. Vertical. We can set this guy equal to 0 and get plus and minus 1 for my x values and my y-intercept. You'll notice degree in the numerator is 1, degree in the denominator is 2, therefore y equals 0. So we go ahead and set up our graph again. Next we'll throw in our vertical asymptotes, which are at 1 and negative 1. Horizontal at 0. We'll label this now. Here's 1, here's negative 1. We have at 3 a x-intercept and at 3 a y-intercept. So now, again, we're going to notice a couple of things. One is that there are no x-intercepts here. Therefore, this part of the graph has to be not necessarily parabolic. It could be any shape, but you know that it's going to go through that point and then eventually not cross these two lines and has to go up because there's no x-intercepts. I have no idea what's going on over here. I'm just going to plug in a negative 10. And I get a negative over 2 more negatives. 3 negatives make a negative. So this graph has to be down here somewhat. Now you'll notice the root here has a multiplicity of 1. Therefore, I know the graph is going to either come from above, cross the axis, and then come back to this, or come from below, cross the axis, and come back down this way. So I have to figure out what's happening at 2. Because that's in between the asymptote and the x-intercept. So at 2, I get a negative on top, and then I get a positive and a positive, which is a negative. So this graph is going to come down here as we stated, come back up, and then loop back down and get close to 0 because that is the end behavior. Okay, so make sure you know those rules. Understand your multiplicities, understand what you have and how you get what you need, and that's basically plugging in points. Okay, the big thing is know how to find your intercepts really well because those are a big indicator as to what a lot of your graph is going to look like. We'll talk again next time.